Hi, this is Calculus 12, Chapter 3.9. We're going to be looking at derivatives of exponential and logarithmic functions. So this is a review of exponential and logarithms, but that'll be in a separate video. If that is not enough help, you'll have to go to Pre-Calc 12 and look for Chapter 5. Okay, e to the x is the most interesting function. And I think I said it before, e is approximately 2.718. So it's an exponential function with a base of 2.718. We can compute e to the x by doing a summation from 0 to infinity of x to the n over n factorial. So it looks something like this, and it goes to infinity. E to the x can also be calculated by taking the limit as n goes to infinity of 1 plus x over n to the power of n. But one of the more interesting things for calculus is the derivative of e to the x is e to the x. So we're going to prove this. However, we need a property, limit as h goes to 0 of e to the h minus 1 all over h equals 1. Or you can look at it a different way. The limit as x approaches 0 of e to the x minus e to the 0 all over x minus 0, and that equals 1. Okay, so our function is e to the x. The derivative, we have to use the limit to prove this. And is it difficult? No, well, let's just substitute. Limit, h goes to 0. It's e to the x plus h minus e to the x all over h. Now, we're used to using the power laws where we're multiplying powers, we add the exponents. This time we're going to go backwards. We have an addition for exponents. We're going to break it up into a multiply. So limit as h goes to 0, e to the x times e to the h minus e to the x all over h. We can see that e to the x is a common factor, so we're going to factor that out. Limit h goes to 0, e to the x times limit h goes to 0, e to the h. When we're factoring out e to the x, we're dividing. That means we have a 1. This is just e to the x. And we said this property is 1. So we just have e to the x. Okay, so that wasn't too difficult. However, we're not asked to do the derivative of e to the x very often. More often, we'll need to use the chain rule. Okay, so if we're doing the chain rule of e to the u, we have e to the u, and then we need the chain rule, du dx. Okay, so let's take a look at this. Derivative of a to the x. It's not as simple as e to the x, but let's look at it. We have d dx. We need to convert a to the x into the form of e to the x. So we start by taking ln of a to the x. So the x comes out front, and we have x ln a. And then we need to do the inverse of ln, which is e to the power of our expression. And that's how we convert it to e to the power of x ln a. So this gives us e to the x ln a. And now we need the derivative of the exponent, d dx x ln a. So this is just a constant times x. So we can put this back in the original form. This is a to the x, and then this is just going to be ln a. So d dx of a to the x is a to the x ln a. And again, if you use the chain rule, we have d dx of a to the u, so we have a to the u ln a, and then we have to use du dx as the chain rule. Okay, derivative of ln x. We need to exponentiate both sides. This is e to the y, and then this is x. And then we're going to do implicit differentiation. So we have d dx, e to the y, and d dx of x is just 1. To differentiate this, we need the chain rule. It's e to the y, and then we have y prime equals 1. So y prime equals 1 over e to the y. So y prime equals, substituting back, this is 1 over x. And that note comes from there. And again, we have the chain rule. D dx of ln u is 1 over u du dx. And again, we're not always dealing with ln x. If we have to do the derivative of log a of x, first thing we have to do is do a conversion. So we do d dx of ln x over ln a. And we just use the log base conversion rules. We're changing from log base a to log base e. This is a constant, so we can pull it out, 1 over ln a. And now we're doing d dx of ln x. And we've already done that. That's just 1 over x. And then we're adding ln a. Again, it's customary to put ln a after x, because if you do 1 over ln a x, it looks like you're multiplying the two together, which is not what you want. Chain rule, d dx of log a of u. We have 1 over u ln a, and then again, we need du dx. So let's look at some examples. Y prime equals e to the minus x over 4. And now we need d dx of negative x over 4. So this is e to the negative x over 4, negative 1/4. And again, we want to write this in common form. Next, y prime equals, so we have 9 to the negative x, we need ln 9, and now we need d dx of negative x. So that's just negative 1, so negative 9 negative x ln 9. Next example. So it's easier to see if we do a substitution. U equals ln x, because we have a composition. That means we're going to use the chain rule, du dx equals 1 over x. So y equals u squared. Y prime is going to equal to 2u times u prime. And this is u prime. Now we substitute everything back in. There shouldn't be any u's left over when we substitute it back in. So we have 2 ln x times 1 over x. And we'll just clean up the notation here. So 2 ln x over x. Please be careful. X's don't cancel. Okay, this is a parameter. This is an expression. You can't cancel a parameter with an expression or term or factor. This is as simplified as it gets. If you canceled and you had 2 ln, this is meaningless because ln is a function. It takes a parameter. Okay, again, let's look at doing a substitution. U equals x plus 1 to the power of 1/2. So du dx equals 1/2 x plus 1 to the power of negative 1/2. And d dx of x plus 1 is just 1. So this cancels out. We may want to rewrite this as 1 over 2 root x plus 1. Okay, going back to this side, we're going to write y equals log base 10. You don't really need the 10. I'm just reminding you that 10 is the base. U. So we have y prime equals 1 over u ln 10. And we need u prime. So we have 1 over. We can also look at this as 1 over 2u. So we have u ln 10, and then we have 2u. So we have 1 over 2. Since u is the square root of x plus 1, now we just have x plus 1, because we have u squared, and ln 10. Okay, one last example. We have an x in the base, we have an x in the exponent. So there's no derivative rule for this. So we do what we did in pre-calc. We need to take the ln of both sides. And if we're taking the ln, this is the exponent, it's going to come out front. Tan x ln x. Well, now we have an implicit equation, so we need to do implicit differentiation. So d dx ln y equals d dx tan x ln x. This is a product. We're going to have to do the product rule. Here we have y prime over y, because the derivative of ln y is 1 over y. We need the chain rule, so that's a y prime. Okay, derivative of tangent x is going to be secant squared x. We need to multiply this by ln x. Now we have tan x, and we need to multiply this by 1 over x, because that's the derivative of this. If you can't remember, we'll have u, v. This is u prime, v, u, v prime. Now we need to isolate y prime. So it's y times secant squared x ln x plus tangent x over x. And now we substitute x tan x back in. Y prime equals x tan x secant squared x ln x plus tangent x over x. And that completes this lesson.